Let's first understand why a vector is broken into components and then see how it is done for a two-dimensional vector. Imagine pushing a heavy box up on a ramp. Part of the force you're applying on the box goes into moving the box forward, and part of the force goes into countering the force of gravity. This example clearly illustrates how a single force applied at an angle actually works along two perpendicular directions. Force in this case is an angled vector. Here's the problem. Working with angled vector directly is messy. Angles make the math complicated. So, what do? We resolve the vector into components. A two-dimensional vector has two components, and a three-dimensional vector has three components. And the beauty of these components is that they are scalars, and it is much simpler to work with scalars. Let's take an example of vector A that is in the first quadrant. The length of the projection of vector A onto the x-axis is its x component, ax, and its value is a positive number. Similarly, the length of the projection of vector A onto the y-axis is the y component, ay of vector A, and it has a positive value. The other way to get the value of the x and the y component of a vector is to use trigonometry. Let's say vector A makes an angle theta A with the positive x-axis. In that case, ax equals a cosine theta A and ay equals a sine theta A. Let's now move to vector B in the second quadrant. Its x component, bx. It is along the negative x-axis, and its y component, ay, is along the positive y-axis. Now, if vector B makes an angle theta B with the positive x-axis going counterclockwise, then bx is simply b cosine theta B, and since theta B is greater than 90 degrees but less than 180 degrees, that means cosine theta B will be a negative number, and hence bx will be a negative number. By, it is b sine theta B, and it's going to be a positive number.